Folks, welcome to another video on logarithms, exponentials, and other inverses. In this video, we're going to be talking about the natural logarithm. So here's the motivating question. We know our power rule for antiderivatives tells us how to find derivatives of functions of the form x to the n, just so long as that power n is not equal to -1. So what happens when n equals -1? It turns out that's going to be related to a new function we call the natural logarithm. So we'll talk about a definition, we'll talk about doing calculus on this function natural logarithm, and then we'll talk about a technique using properties of logarithm called logarithmic differentiation. So here's a definition. The natural logarithm of x is given by ln of x, and it's found by doing a definite integral, the definite integral from 1 to x of 1 over t dt. So this is something that we can understand naturally because we can graph the function 1 over t, and we can think about finding the area under the curve from the value 1 to the value x. So again, we can think of this as the area under the curve 1 over t from 1 to x, and certainly we need x greater than or equal to 0 because 1 over t is discontinuous at 0, so we don't want to pass through that point. So in particular, when x is greater than 1, like over here, I'll choose the x value to be over there nearby 4. The log of x, or the natural log of x, is given by this area. And of course, when x is a number that's between 0 and 1, we instead think about integrating from 1 back to that number. And we can see that the area under the curve, I guess, is positive, but since we're integrating from 1 backward to x, from right to left, we can see that the natural log of x is going to be negative if x is any value between 0 and 1. From this definition, we can see a lot of properties. Here's the first one. The natural log of 1 is 0. This is quick to see just by the definition. So again, by definition, the natural log of 1 is the integral from 1 to 1 of 1 over t dt. And we know that if we have a definite integral whose endpoints start and stop at the same point, the value of that definite integral is 0. Here's another property. The natural log of 1 over x is minus the natural log of x. So let's go ahead and see that again using the definition. So here's our u substitution. Our u substitution is u equals 1 over t. From that, we can compute du as minus 1 over t squared dt, or dt can be written as minus 1 over u squared du. Of course, when t is 1, u is 1, and when t is 1 over x, u is 1 over x. So we can see that we can write this definite integral in u world as the following. So substituting and simplifying, we can see that the natural log of 1 over x can be written as the integral from 1 to x of u times the quantity minus 1 over u squared du, or pulling the minus sign out front and writing u times 1 over u squared as 1 over u, we can see that the natural log of 1 over x is written as minus the integral from 1 to x of 1 over u du. Now this, as it turns out, is exactly minus the natural log of x. And the reason for that is because the definite integral sitting right there in front of you is exactly the definite integral, albeit in u world, that represents the natural log of x. Okay, so lots of other properties of the natural log follow. There are other properties. The natural log of a product is the sum of the natural logs. The natural log of the quotient is the difference of the natural logs. And the natural log of a power is n times the natural log. So we'll use these properties a lot, and we'll use them to simplify natural logs, so you should be familiar with them. The derivation of all these properties follows exactly from the definition, and then properties of the definite integral. Okay, let's go ahead and talk about the end behavior in the graph. We saw that the natural log of x is positive when x is greater than 1, negative when x is between 0 and 1, and it turns out that the natural log of x goes to infinity as x goes to infinity, and minus infinity as x goes to 0 from the right. So finally, it turns out that the graph of the function f of x equals ln of x is always increasing, or we say that's monotonic increasing. So the graph of that function looks like the following. So again, that graph goes to negative infinity as x goes to 0 from the right. It goes to positive infinity as x goes to infinity. The natural log of 1 is 0. And you can imagine from the intermediate value theorem that there's some value over here where the natural log is equal to 1. And for reasons that will become apparent later, we're going to call that value e. It turns out the value e is about 2.7, blah, 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 blah. So the natural log of e is 1. And again, we'll come back to that value of e later on. Okay, let's go ahead and talk about doing some calculus on this function, natural log of x. We can see that the form of the natural log function is defined exactly as the form of a function for the fundamental theorem of calculus. Therefore, we should be able to use the fundamental theorem of calculus to look at the derivative of the natural log of x. So here's that derivative. The derivative of the natural log of x is 1 over x. And now we can see the answer to our original question regarding the power rule with n equals minus 1. It's the derivative of the natural log of x who has power minus 1. Okay, so here we see the base derivative. The derivative with respect to x of the natural log is 1 over x. And the corresponding chain rule, the derivative of natural log of a composition is 1 over the inside times the derivative of that composition. Let's go ahead and have a look at some examples. Here's an example. Let's find the derivative of the natural log of x squared plus 1. And we'll go ahead and just use the chain rule here where the inside function is x squared plus 1. So using the chain rule and simplifying, we see that the derivative is 2x over x squared plus 1. Here's another example. Let's find the derivative of the natural log of 7x. Now we can go ahead and just use properties of, or the chain rule here as well. And perhaps surprisingly, when we simplify, we see that the 7's cancel and the derivative of natural log of 7x is exactly 1 over x. Now that may seem unusual, but it turns out it's not, and we can use properties of the natural log to show why this is true. Remember that the natural log of a product is the sum of the individual natural logs. In this case, we can express g of x, log of 7x, as log of 7 plus log of x. So just use the derivative, and remember that log of 7 just means the area under the curve 1 over t from 1 to 7. That's a constant number, so the derivative of a constant is 0, and we end up with g prime equals 1 over x. So using properties of natural logs like this is going to help us in finding derivatives, and we'll see a little bit more about that later. Here's another example. Let's find the derivative of the natural log of x. So again, just using the quotient rule, or sorry, the chain rule here. So the derivative in this case is 1 over the natural log of x times the derivative of the inside function, which again is natural log of x. And it's common when we have products of x and natural log x to write the x first, so I'm going to express this as 1 over x times ln x. Here's one more example. Let's go ahead and look at the derivative of the natural log of minus x, and you can imagine that this looks like we're taking the natural log of a minus function, which wouldn't be allowed, but here the domain, the natural domain, would just be implied to be x less than 0. So perhaps not surprisingly, given our intuition on the derivative of the natural log of 7x, the natural log of minus 1 times x is also 1 over x. So this leads us to something kind of interesting, which is that the natural log of the absolute value of x is the natural log of x when x is greater than 0, and the natural log of minus x when x is less than 0. So we can see now the derivative of this function. The derivative of this function is 1 over x when x is greater than 0, and 1 over x when x is less than 0. So it turns out that the derivative of the natural log of absolute value of x is 1 over x. And we actually use this in our corresponding anti-differentiation rule. So since 1 over x can be found by taking the derivative of the natural log of x, the antiderivative, the general antiderivative of 1 over x is the natural log of x plus c. And again, this is sort of the most general antiderivative that encompasses all of the possible domain values for the function 1 over x. So here's an example. Let's go ahead and have a look at the integral, the indefinite integral of this case of cotangent. So cotangent isn't a function we deal with a lot, but we'll start by writing it as cosine over sine, and then see that there's a substitution that can help us. So with the substitution u equals sine of x, we can see that du is cosine of x dx, and this indefinite integral can be written in u world as the integral of 1 over u du. So we'll go ahead and express this in terms of the natural log, and then go back to x world to see what the general antiderivative is. So the antiderivative, general antiderivative of cotangent of x is the natural log of sine of x plus some constant. Let's do another example. Let's go ahead and evaluate the definite integral, the natural log of x over x from 1 to e. So again, here's something that doesn't exactly look like our antiderivative rule. However, we can use a u substitution to simplify. So look for a function as derivative. In this case, we see the function natural log of x has derivative 1 over x. So here's our substitution, u equals ln x. We can find that du is 1 over x dx. Of course, substituting the limits also, when x is equal to 1, u is the natural log of 1, which we know is 0. And when x is equal to e, u is a natural log of e, which we now know is 1. So we can quickly write this definite integral in u world using these new limits and function. So once we make the substitution, the definite integral is evaluated quickly with the fundamental theorem of calculus, and we can see that the value of the definite integral is 1/2. So let's go ahead and have a look at logarithmic differentiation. The strategy behind logarithmic differentiation is to use properties of the logarithm first to simplify, and then use calculus on the simplified version. So here are the properties we'll be using, primarily the natural log of the product, the natural log of the quotient, and the natural log of a power. So again, the idea is to simplify and then evaluate the derivative. And a quick tip here, logarithmic differentiation typically involves using implicit differentiation also. So here's an example. Let's go ahead and find the derivative of this function that's a quotient of polynomials, and then the square root of that quotient. And we'll start off by simplifying it with the natural log. So in simplifying the natural log of this expression y, I've used two rules. First, I've used the power rule for logarithms to hop down this power in front. And second, I've used the quotient rule for natural log of a quotient to write the quotient as a difference. So we can see that the natural log of y when y is powers and products and quotients, the natural log of y will be just sums and differences, which is much easier to differentiate. So let's go ahead and look at the derivative of the natural log of y, and again, we'll use implicit differentiation here. So we can see that differentiating natural log of y with respect to x gives us 1 over y dy dx. That's just implicit differentiation from Calc 1. And then we can take the derivative of the right-hand side here quickly, because the natural log of x squared plus 1 and the natural log of x squared plus x to the fourth plus 1 are quick to differentiate. Now remember here, we're trying to find the derivative dy dx, so go ahead and solve for dy dx, and remember we know what y is originally. So here's that derivative, dy dx is 1/2 times the square root of the quotient x squared plus 1 over x to the fourth plus 1. That's just y, of course, and then multiply by the sum of those two rational functions, 2x over x squared plus 1 plus 4x cubed over x to the fourth plus 1. And again, this quantity just comes from multiplying both sides by y above. Okay, folks, hope you've enjoyed this video on the natural logarithm. Have a great day, and we'll see you next time. Bye-bye.